We'll start out with a quick background on the Davis-Besse reactor plant. The Davis-Besse reactor plant is located 21 miles east of Toledo, Ohio. It is operated by First Energy Nuclear Operating Company. It is a 889 megawatt reactor, and it began commercial service on July 31st, 1978. Davis-Besse discovered borated primary water had leaked through stress curves and cracks in the wall of an A600 nozzle. They also discovered boric acid wastage on top of the reactor vessel head. Approximately 900 pounds of boric acid residue had leaked out and resided on top of the head. Corrosion had already occurred through 6.5 inches of steel, and only a third of an inch of stainless steel cladding remained as a pressure boundary, keeping 2,100 pound reactor coolant from leaking out of the reactor vessel. The stainless steel cladding did exhibit plastic deformation in the form of a 1/8 inch bulge. The damage at Davis-Besse can be traced back to the cracks in the nozzle caused by stress corrosion cracking of the Inconel A600 nozzle. The crack initiation began around 1990, and the leakage from the nozzle began around 1995. The cracks allowed borated primary water to leak through the cracks and come in contact with the low alloy steel reactor vessel head. The boric acid wastage of the low steel led to the creation of a large cavity approximately 6.5 inches deep and 5 inches wide in the reactor vessel head. This is a view of the top of the reactor vessel head at Davis-Besse. In this picture you can see the boric acid deposits and corrosion on top of the reactor vessel head. This is a picture of a 17-inch diameter section removed from the Davis-Besse reactor vessel head, showing the boric acid wastage around nozzle 3 toward nozzle 11. Davis-Besse was left with no other option but to replace the damaged reactor vessel head. The plant had to purchase a replacement head from Midland, an uncompleted reactor plant. The total cost of the repairs added up to $600 million, and the plant was shut down for 2 years pending approval from the Nuclear Regulatory Commission. Although the repairs did not take 2 years, Davis-Besse had to prove that they could operate the plant safely. Could Davis-Besse prevented this incident? First off, these were good engineers, doing the best that they could with the information they had at hand. Although this incident shares a lot of the same factors that led to the devastating Challenger disaster in 1986, the engineers at Davis-Besse did not have near as much information as the personnel at NASA had. The engineers did miss indications such as the amount of boric acid on the reactor vessel head, the changes in the boric acid deposits, the frequency at which containment radiation monitors were becoming clogged, and that the nozzle was made from a very susceptible heat of material. With these missed indications, I'll also be discussing the normalization of deviance, or gradual process through which unacceptable practice or standards become acceptable. The first misindication that Davis-Besse had that a bigger problem was occurring at their plant was the boric acid deposits on the reactor vessel head. Boric acid deposits were first discovered in the early 1990s and were cleaned over the next couple of years. Davis-Besse self-identified the source of these deposits were leaking flanges. All flange gaskets in the plant were replaced in 1996, and Davis-Besse did not question other possible sources when the deposits continued after 1996. Furthermore, they knew that the access for visual inspection of the reactor vessel head was limited due to the blocked inspection ports called mouse holes, and it was determined by management that the cleanup could be pushed until 2002, even with concerns from engineers. It was during the next shutdown in February of 2002 that Davis-Besse discovered 900 pounds of boric acid deposited on the reactor vessel head. The second indication that was missed by Davis-Besse was the observed changes in the boric acid deposits. Even though the deposits changed from powder to hard deposits and contained some regions of rust-colored deposits, the plant still decided to continue operations. The third missed indication in this incident is the clogged filters on containment radiation monitors. The cleaning frequency of these filters increased from once every 30 days to once every 3 days. During cleaning, Davis-Besse also discovered that rust-colored deposits were on the filters. The clogging of the filters continued after the plant moved the monitors away from the exhaust fans and also added HEPA filters. The fourth missed indication was the fouling of containment air coolers. Original cleaning schedule prior to November of 1998 was once per refueling outage. Cleaning of the air coolers then increased to 17 cleanings over the course of the next 7 months. After repairs were made to the air coolers, cleaning went down to once per month. Davis-Besse removed approximately 75 gallons of wet boric acid from the system during these repairs and still attributed this to a flange leak. They attributed this to a flange leak due to historical experience in commercial plants. Engineers at Davis-Besse still attributed the clogging of the air coolers to leaking flanges even though all the flange gaskets had been replaced in 1996. They also did not question the rust deposits found and rust on other components in the containment vessel. The changes in the cleaning schedule were likely due to changes in the nozzle crack size. Engineers again lacked a questioning attitude with this missed indication.
The final missed indication was the susceptible heat of material used in the manufacturing of the nozzles. Some of the nozzles at Davis-Besse were manufactured from heat M3935, which was more susceptible to stress corrosion cracking. 20% of the nozzles manufactured from this heat cracked compared to an average of 13% from other heats. The normalization of deviance from this indication is that engineers depended on predictions rather than actual experience.
There are also other contributing causes to this incident. Management monitoring did not identify problems in changing conditions in the plant. There was inappropriate elevation of concerns. They lacked independent oversight in the plant. Assessment of all reasonable potential causes were not systematically proven or disproven until the cause was identified. Operational pressures influenced technical decisions, and assumptions for technical decisions not verified by direct inspection. You can compare some of the mistakes Davis-Besse made to the mistakes NASA made with the Space Shuttle Challenger disaster on January 28, 1986. Management at NASA was concerned with maintaining the operational schedule and did not want to delay the launch even though engineers expressed their concerns about the O-ring failure in colder temperatures. Management at NASA also did not believe the possible O-ring failure would cause any significant damage. Davis-Besse made similar mistakes. Management at Davis-Besse was more concerned with getting back to production and did not want to delay production for the cleanup of the boric acid deposits, even though engineers had expressed concerns of the need to finish cleaning these deposits. Davis-Besse chose to delay the cleaning because they did not believe significant damage could occur to the reactor vessel head prior to the next inspection.
The Davis-Besse incident brought about many changes with how the Nuclear Regulatory Commission conducted business. You can see these changes in the inspection program, the integration and assessment of performance data, communications, this includes the plant reporting process and how the Nuclear Regulatory Commission disseminates information, and also in the licensing process guidance.
Davis-Besse self-identified the following in the root cause analysis report they released on April 15, 2002. Analysis identified that several opportunities for identification of and scoping the significance of field conditions were missed when reviewed collectively. The relating of independent but common causal data was missed at all levels of the organization.